Okay, so welcome everybody to the morning seminar today, and Mark van Raamsdonk will be our speaker, and who is very well known, and he has given many seminars on the already in the various Indian channels. But today he is going to talk about something he has probably not talked about very recently. It is his new work from getting cosmology from confining gauge theories by holographic models. And so over to Mark. Let's hear about it.
Okay, so yeah, thanks very much for the invitation. And I mean, thank you all for coming. I've been sorry to read about the situation in India recently, and I can imagine it would be very hard to focus on physics. But anyways, hopefully I can tell you something interesting. And so the topic of the talk is basically, how can we try to use ADS-CFT, which is our best model for quantum gravity? How can we use this to understand one of the most important questions in quantum gravity, which is how to understand cosmology and the Big Bang? And so, of course, usually in ADS-CFT, we're limited to kind of understanding physics in spacetimes that are sort of boring asymptotically. So asymptotically ADS spacetimes, they could have lots of interesting things in the interior, black holes and whatnot, but out at near the asymptotic boundary of spacetime, then things are just empty and negatively curved. And so this is not really much like our own universe that we observe. And so it's hard to see how we could connect these two things. And in this talk, I'm going to suggest a possibility that we might be able to actually describe kind of ordinary cosmological physics, perhaps not yet realistic, but some kind of four-dimensional Big Bang, in this case, Big Crunch cosmology, using just ordinary ADS-CFT. So just with the standard setup. And so in the first couple of slides, I'm just going to tell you the basic picture, and it'll seem maybe a little bit weird or unmotivated. And then I'm going to go back and talk more about the motivation for what I'm saying and try to convince you that it might be true. Okay, so as you know, when we have the ordinary ADS-CFT correspondence, we have some conformal field theory, say on, let's say, a sphere. It could be R3. And so in order to describe this four-dimensional cosmology, I actually want to start with this situation of a four-dimensional field theory. So it's a little bit different from what we might think. But I want to consider some particular high energy state of this CFT. Okay, so the dual of this is going to be an asymptotically ADS spacetime, but it's a very high energy state. And so this on the gravity side is going to look like some kind of black hole geometry. Okay, from the outside, from the point of view of this asymptotic region, this state is going to be dual to a geometry that looks like it has a large black hole. Okay, but the interesting cosmological physics is actually going to be behind the horizon of the black hole. So this is a space-time diagram of this black hole geometry where you see the exterior region, and the green is the asymptotically ADS region. And the idea is that for this very special kind of state that I'm going to describe in the next slide, that the black hole geometry actually has something interesting in behind the horizon. If you go past the horizon, eventually you get moving spatially to some inner boundary of the space-time. So this is what's indicated in red. And of course, this diagram is suppressing the sphere or R3 directions. Okay, so this is a four-dimensional geometry. And so I'll call this an end of the world brane, just that because it's some inner boundary to the space-time. And I'll talk more about the physics of what this brane is. But the thing that you can notice is that as a function of time, this end of the world brane, it starts at the past singularity in this black hole geometry, and it ends up in the future singularity of the black hole geometry. And so what happens is that it actually, let's say if we're talking about the S3 case, it's spatially in S3, but it starts out with 0 size, expands, and then contracts again. So the intrinsic geometry of the end of the world brain is like a big bang, big crunch FRW spacetime. Okay, so normally that wouldn't.
Mark,
Oh yeah,
can I ask
yeah, go
something
ahead.
here already?
Yeah, please.
It looks like more or less a microstate of a black hole, except that it is there is some kind of time dependence here.
Yeah, so it's not an energy eigenstate, and so it's indeed just what we think of as some particular microstate of the black hole that is maybe a combination of energy eigenstates, so that it can have some time dependence.
I see. So it's like somewhat similar to this solutions of the BFSS matrix model, which has very mild time dependence, because a typical state will have all the it will be fully Higgsed. UN would be fully Higgsed, and you will have very small time dependence. So it's like a slowly evolving microstate. You know.
Yeah, I mean, from the point of view of right, from the point of view of the CFT, actually many observables will just look thermal. But then if you look at, I guess, certain things, certain entanglement entropies, for example, will have some time dependence. And there are some interesting phase transitions and so forth. But yeah, so from many points of view, it looks kind of static and just thermal, but there's definitely time dependence that's important. And so that's reflecting this behind the horizon physics.
Yeah, thank you. This is analogous to the SYK, pure state SYK picture to some extent in that way.
Yeah, that's right. In fact, it was partly motivated. This whole setup was motivated partly originally by the work of Kurkulu and Moldesina on the pure state SYK model. Okay.
Thank you.
Great. So far this wouldn't be like particularly interesting for cosmology, because this red region is just like the inner boundary to the space, and so we wouldn't really expect there to be some intrinsic gravitational physics living there. This is just a boundary in say a 5-dimensional space-time. So we need an extra bit of physics, which is the physics of Randall-Sundrum cosmology, or the physics of what are called Cartrandal brains. And so this is the idea that sometimes in certain situations, when you have a brain, then you can have gravity localized on that brain. And so in the context of asymptotically ADS geometries, it's known that if you have a brain that kind of cuts off the UV of an asymptotically ADS spacetime, then some mode of the bulk 5D graviton actually kind of localizes on the brain. And then over some range of distance scales, you would actually see 4-dimensional physics if you were, say, an observer living on the brain performing some experiments. Okay. And so that's the idea here, that in certain cases, for certain choices of states, maybe this end of the world brain is actually very far behind the black hole horizon and can be understood as cutting off the asymptotically ADS spacetime that forms the second asymptotic region. Okay. And so in this case, we might be able to have gravity localize on this end of the world brain. And then we would have not only a geometry that's for the end of the world brain, that's a 4D FRW Big Bang Big Crunch geometry, but we would also have 4D gravity. So we would have the effective description would be 4D cosmological physics. Okay. And later, I'm going to talk about the possibility that in some cases, maybe this entire 5-dimensional part of the geometry, it might not be that, it might be that that's, say, strongly curved. So in some cases, it might be that the only like really geometrical part of this entire picture is this end of the world brain. And then it would be even more like 4D cosmology, because the 5D part is kind of strongly curved and non-geometrical. Okay, and that would be the situation if the CFT that we start with is maybe not a conventional holographic theory. Okay, but we'll understand that much better later on. Okay, so before we get on to the motivation, I want to tell you specifically what kind of state I'm talking about and how do I build this thing. And so this kind of state that I'm talking about is something that I construct using a particular Euclidean path integral. So we learn in quantum field theory courses that if I want to construct the vacuum state of a quantum field theory, then I can use a Euclidean path integral on a semi-infinite amount of Euclidean time. And you would say that the wave function, the vacuum wave functional for your quantum field theory, evaluated on some field configuration phi 0, is just equal to the integral over all the field configurations on that semi-infinite cylinder with this boundary condition. So that would be for the vacuum state. Now, the states that I want to talk about are not the vacuum state, but the construction is similar. And so the construction in this case involves cutting off the cylinder at some previous Euclidean time. And now at this past Euclidean time, I'm going to couple my 4D CFT to some three-dimensional Euclidean holographic CFT. So we have extra field theory degrees of freedom living down here in the Euclidean past. And I'm actually going to choose this theory to have many more local degrees of freedom than the 4D theory. Okay, so maybe there are a lot of fields here at this past Euclidean time, relatively few fields here. And that's going to actually be related to the gravity localization. Okay. So how do we get a state out of this picture? Well, it's sort of just the same way as before. If I want to evaluate the wave functional for my state on some field configuration on the sphere, I just integrate over all possible field configurations of the 4D fields and also these 3D fields, and these are coupled together somehow. And then I weight it by the action for this combined theory. Okay. And so I'm going to give you some explicit examples of this kind of theory later on in the talk. So somehow the idea is you're using a very complicated three-dimensional Euclidean field theory as part of the construction of the state. And that ends up constructing a very interesting state of your CFT that ultimately ends up having this interpretation that I described. Okay, so let's step back now and talk about some motivation for this whole picture. And so one motivation is an observation of Maldacena and Maus from close, I think 15 years ago already. And so basically they noticed that certain cosmological spacetimes with a big bang and a big crunch, if you analytically continue the time direction, then you can get an asymptotically ADS spacetime. But an asymptotically ADS spacetime with an asymptotically ADS region in the Euclidean future and in the Euclidean past. Okay, so this kind of spacetime is an asymptotically ADS Euclidean wormhole geometry. Okay. And so they said, well, if we want to describe cosmology, maybe a good starting point would be to understand how to describe these asymptotically ADS Euclidean wormholes in ADS CFT. So they asked this question: how do we build such a wormhole? And because these spacetimes have two asymptotically ADS regions, then it's natural to think that the field theory dual should involve two three-dimensional conformal field theories, holographic conformal field theories. But because this whole setup is Euclidean, we run into this now famous factorization issue. So if I just think about a Euclidean field theory on a sphere and then another one on a separate sphere, and these two things are not interacting, then the partition function for this theory and all of the correlators will factorize between the two copies. But if I try to do a gravity calculation here of some correlator, then the connected geometry here will imply that the correlators don't factorize. So Maldacena and Maus discussed this puzzle, and by now we have various ideas for how to resolve this. So one idea that we've understood recently to be correct in the context of JT gravity and other simple models of gravity is the idea that instead of this geometry being dual to a particular CFT on this pair of spheres, maybe the geometry here is actually dual to some ensemble average, that the instead of just the partition function for the single CFT, you take the product of partition functions, but then average that over an ensemble of CFTs, and then maybe that is the thing that this gravity solution is describing. So that's one possible resolution for the factorization problem, because in the ensemble average, correlators don't factorize. Another possible resolution is the idea that maybe these two CFTs are actually just interacting with each other in some subtle way. Maybe there's some kind of soft interaction between the two CFTs, and this leads to the correlators between the two sides.
And Mark, can I ask something?
Yeah.
So here we are assuming that there will be a big crunch, but suppose if our universe was open, then there is this, we cannot use such analytic continuation to describe cosmology.
Yeah, that's right. So what I'm talking about today, so far, I don't know how to do the situation where there's not a big crunch. So I'm just at this point happy if I can get a big bang and then some evolution after that. And then in these models that I'll describe, it looks like you have a big crunch. Of course, it's possible logically that even our own universe at some point will have a crunch, and it's not ruled out. We have very poor understanding of dark energy and many aspects of cosmology. So I'm just kind of more or less satisfied at this point if I can just get any model of cosmology with a big bang that I can study microscopically, and then maybe if either you modify that somehow, or you're secretly hopeful that our own universe sometime has a big crunch.
Yes, but just I have a little stupid question here. So how does this usually work? I mean, we should be able to describe arbitrary initial conditions or something, right? In this, when we go from here to here. So when this, so a little bit, the question is more of this. Are we able to describe, for example, what would have happened if I would have changed my initial conditions a bit? And I mean, we know this it requires a lot of fine tuning and everything, right? So if we had, what will go wrong here in this?
So I mean, here the picture is that we have one particular field theory set up. It's going to give us we will have some choices about, so going back to this, we have some choices about which 3D field theory we pick. I mean, we have some choices that we can make, but once we make those choices and decide on the Euclidean theory here, then this should give you sort of the complete description of the cosmological physics. And I think it may be that this wave function here, rather than, so that should correspond to some gravitational wave function. And it's likely that that gravitational wave function corresponds to some, superposition of possibilities as we would expect. But that's the prediction it makes would be then these are the possibilities for your cosmology. And so it would probably be, some kind of ensemble of universes, and maybe we're just one of the typical ones in that ensemble. So I think the idea here is we want to come up with a microscopic picture and then just ask what are the predictions of that particular microscopic picture for the typical cosmology that it describes.
So this ensemble is simply not coming out from tracing over other possibilities, which doesn't lead to big crunch, for example. This is a which you can't say anything about it, but how this ensemble averaging itself arising from quantum gravity. But
sorry, when I just said the word ensemble, I really meant just meant that the wave function here would be a superposition of different possibilities. So it's a pure state, and then in terms of interpreting that for gravity, there may be some, if we think of maybe the bulk modes here as some environmental degrees of freedom, and we trace over those, leaving just the wave function that would be relevant for the end of the world brain, then I think that will be sort of an ensemble or a density matrix, I guess I should say, with maybe different possibilities for the detailed cosmology.
I see. So you think that maybe this, you could think that this averaging that you are getting of the CFTs might be a reflection of somehow the fact that you're blind to the other possibilities which don't lead to big crunch, for example. So you're
well. Let me continue with this, because I'm about
okay.
to tell you that I don't want to do averaging. So in this Euclidean picture, I actually don't want to do any averaging. So I said, that's one possible resolution of the factorization problem. But another resolution is that these are just interacting somehow. And so, so my resolution, or the thing that I'm proposing, is that to get this wormhole, we start with, say, a picture of these two 3D CFTs that would be associated with the asymptotic regions. But then I'm going to actually couple the two 3D CFTs with some auxiliary degrees of freedom. And this is actually the 4D CFT that I was starting with. Okay, so this is a different motivation for that same basic picture I had before. So now I guess the Euclidean continuation of the cosmology is dual to this field theory that has a boundary, a 3D theory up here, a 3D theory down here, and then some 4D theory on a finite cylinder in between. Okay, so this is a field theory. Most of the degrees of freedom are in these holographic theories on the two boundaries. And if you integrate out these auxiliary degrees of freedom, then the resulting thing kind of looks like an ensemble average. But really, the full theory is just one interacting quantum field theory. Okay, so the proposal is that taking two holographic CFTs, and still we're in the Euclidean picture. So we have these two Euclidean theories, you couple them this way, and I want to claim that the effective description of the physics is some 4D asymptotically ADS Euclidean wormhole.
Your sources are coupled in some specific way, or there's some weighting function of the sources, which is not factorizable?
Yeah, let's see. So this picture, let me explain this. So the idea here is that if I calculate the partition function for this full theory, then it actually looks like, so these auxiliary fields, they couple to the 3D CFTs on the two boundaries. And so the auxiliary fields look like sources for some operators in theory 1 and theory 2. And so that's what the J1 and J2 here are, the auxiliary fields evaluated on the two boundaries. And so then when I do the path integral over so I just do the field theory path integral over the auxiliary fields, that will then generate some kind of measure or like probability distribution for the sources at the two ends. Okay, so just formally speaking, I can rewrite the full partition function as an ensemble average, or not, well, as some kind of an average of the original 3D theories with sources, where there's some probability distribution for the sources. So the sources in this case, they're different between the two sides. And so it's not like a true ensemble average, but it's similar to an ensemble average. If I set J1 to J2, then it would be an ensemble average. And so the idea, so one thing we can notice is that there's this parameter tau 0, which is how close the two sides are. And if I have sources that are, say, weakly correlated, so if this is large, if this tau 0 parameter is large, then like the green fields on the top boundary are only going to be weakly correlated with the fields on the bottom boundary. And so in this case, we expect maybe the two 3D CFTs aren't really correlated much at all. And so in this case, I might expect there not to be any connection between the dual spacetimes. But if I take this tau 0 parameter to be small, then we're going to get some strong correlations between the two sides. And this is then more like the ensemble average, where J1 is equal to J2. And I'm going to argue that in that case, in that limit, then we might expect to get a wormhole. Okay. So, all right. So far in this picture, theory 1 and theory 2 were supposed to be holographic 3D quantum field theories. And then the green degrees of freedom, I wasn't really assuming anything about them. Maybe they're holographic or maybe they're not. But let's, for the moment, assume that those green ones are holographic as well. Okay, so now we're imagining this field theory on a cylinder where everything is holographic. And so then we expect that either of these pictures is going to have some dual, say 5D geometry. And so in this 5D geometry, then there should be, because the field theory has these two boundaries, then that boundary should be reflected in the bulk somehow. And the picture is that there's going to be some kind of end of the world brain that is approaching the CFT boundary when you go to the asymptotically ADS region. But we have these two natural topologies for that end of the world brain. Okay, so I'm just asking, what is the Euclidean gravity dual for this cylinder? And so one possibility is that it looks like this, which is like some of the ADS cylinder with caps on the end. Okay, so that's a disconnected end of the world brain. But then another possibility is that this end of the world brain actually connects from top to bottom. And so the green region is still like asymptotically ADS, but then as you go in the radial direction, you get to this end of the world brain. And so this is the configuration that I'm interested in. So you see in this second configuration, the red region, which is this end of the world brain, it does have the geometry of a wormhole. And I'm going to argue that if the degrees if there are like a lot more degrees of freedom on the top and the bottom here than in the middle, then gravity is going to be localized to this wormhole. Basically, because the original theories are 3D CFTs, their gravity dual would be some 4D theory. And if I'm just kind of perturbing that a little bit by adding a few degrees of freedom that couple the two sides, then I might expect that you retain the 4D character of this theory that describes this end of the world brain. Okay.
I see, but there will be some maybe contributions also coming from the other, and although it might be suppressed, but
yeah, that's right. There's something there. There's some kind of 5D bulk still. So we're not what we're ending up with is some kind of like Randall-Sundrum type of scenario, rather than just a completely conventional wormhole or cosmology.
I see.
All right. So we want to, we want to make these number of degrees of freedom very small so that perturbation is as small as possible. But we still need enough correlation between the two sides in order so that the dual gravity, this connected solution is preferred, because this is the one we want. This is the wormhole that's going to continue to our cosmology picture. Okay. Okay, so now I want to connect with this. In my title, I had cosmology from confinement. And so I want to argue that this connection between the two sides, the formation of this wormhole actually has something to do with the physics of confinement in field theory. And so I've argued that in order to get the strongest correlations between the two sides in the field theory picture, we want to take this tau zero parameter to be very small. And so if we're dealing with conformal field theory, so that tau zero and the radius of this sphere are the only parameters, then taking this limit where tau zero becomes small is equivalent to taking a limit where the sphere becomes very large. So I want to study that limit. So in that case, the sphere becomes R3, and then our field theory is just a planar three-dimensional theory on R3 and then another one, and then these are coupled through a strip of a 4D CFT. Okay. So it's like a four-dimensional, the microscopic picture of this field theory is four-dimensional, but at long distances, we expect that this should flow to some three-dimensional theory. Okay, so long at distance scales much larger than the separation here, then we're going to be described by some three-dimensional physics. Okay, and so we could ask, what is this? What is infrared physics? And so two natural possibilities for the infrared physics of this model would be that either there's some non-trivial fixed point, and we have like excitations at arbitrarily low energies. And in this case, that would be a CFT in the infrared. And so in that case, the gravity picture by the usual ADS CFT dictionary, the gravity picture should have a radial direction that just continues to go into the infrared. The other possibility, which is perhaps more generic, is that this 3D theory that we're going to flow down to is gapped. And so in that case, what we expect from ADS CFT, the gravity dual of a gapped theory is one where you go in the radial direction, and then at some point you hit an infrared boundary of your space-time. Okay, and so in this setup, a very natural way for that to happen is this picture where the end of the world brane from the top boundary actually joins up with the end of the world brane from the bottom boundary. Okay, so you see it in this case, which corresponds to my second scenario here, where these join up. So in this case, you see that there's only so far you can go in the infrared, and then you hit the wall. And so this corresponds in your field theory to having a gap theory in the infrared. Okay, and so this is the kind of cosmology from confinement. If you have an example like this, where you get this picture, okay, which corresponds to a confining gauge theory, then you see that this end of the world brane connects up between the two sides.
Mark, isn't it very similar to this chiral symmetry breaking scenario in, say, Sakai Sugimoto, where you have this, here you can think of this as two BCFT type branes, and which actually join together and then into something connected, and then that causes confinement. And or in that case, of course,
that's right. It's very similar. And actually, I'll mention some other early precursors of Sakai Sugimoto later in the talk, because my microscopic construction is actually going to involve some branes from string theory. So far, this is sort of some generalities, and then I'm going to talk about a more microscopic construction soon. Okay, so let me just maybe summarize then. I'll summarize the Euclidean picture of how to get this Euclidean wormhole, and then I'll summarize how that connects to the cosmology, and then we'll talk about the microscopic construction. Okay, so the idea is, in order to generate this Euclidean wormhole, I'm going to generate a wormhole which is at the which is really a kind of brane at the boundary of a 5D spacetime. But I'm going to argue that gravity is actually localized on that brane. And so the field theory dual is just that you have these pair of 3D CFTs, Euclidean CFTs. They're coupled via a 4D CFT, which has many fewer degrees of freedom. And then, the idea is that that maybe generically, when you have such a thing, this 3D physics in the infrared would be expected to be gapped, and in the gravity picture, that confinement or that mass gap comes from the fact that you have an infrared boundary, and I'm going to argue that is understood as these end of the world branes joining up. Okay, and so while this entire geometry it's really a 5D geometry, if there are many more degrees of freedom on these boundaries, then it should be something like 4D physics with a small perturbation. And so that the interpretation is that it's mainly 4D physics localized on this brane, but then some things could leak off into the 5D world. Okay, and so once I have that Euclidean picture, so the Maldacena-Maus idea is somehow, well, if we could analytically continue that, that would give us the cosmology. But I can be a little bit more precise about what the meaning of this analytic continuation is. And so that's what gets us back to the original picture. So the idea is if we take this Euclidean theory and we think of this path integral and then slice it in half, then the bottom half of that path integral generates a state of a Lorentzian 4D CFT. So just like I described, generates the wave functional for some 4D CFT state. Okay. And then we could ask, like, what is the gravity dual of that state? Okay, so the gravity dual of that state, to understand that, you take this Euclidean theory, and you also can think about the saddle point geometry that we get there, slice that in half, and think of that as that then serves as the initial data for some Lorentzian evolution. So this is like the kind of standard ADS CFT way of understanding the gravity dual of a state that you prepare by a path integral like this. You look at the Euclidean picture, construct the dual Euclidean geometry, slice it in half, and then the geometry on the slice is the initial data for your Lorentzian evolution. And so if you do that in this, starting from this picture, then you get a geometry like this, which is the one that I showed in the first slide. Okay, so these kind of state in this construction, if we manage to get the wormhole in the Euclidean picture, then you get this end of the world brain in the Lorentzian picture, whose geometry is the FRW Big Bang cosmology. Okay, so let me talk about a microscopic model. So I want to tell you a construction within string theory, and then I'm going to motivate further the fact that this end of the world brain connects up, and tell you more about what this end of the world brain actually is in the context of string theory. So as a microscopic example, I'm going to start with our favorite example of a holographic theory. So my 4D CFT is going to be n equals 4 supersymmetric Yang-Mills theory. And so that's the theory that's going to be in the middle here. And now I have to tell you, what are the theories that I couple this to at the two ends of the interval? And so what I'm going to do is use 3D theories that can couple in a supersymmetric, that can individually couple in a supersymmetric way to n equals 4 super Yang-Mills theory, just because that is going to give me the most control. But then ultimately I will be breaking supersymmetry. Okay, the combination of the two boundaries will break supersymmetry. So for now, let's just focus on one boundary. And so let me tell you about these special three-dimensional superconformal field theories that you can couple to n equals 4 super Yang-Mills with preserving half of the supersymmetry. And these come from certain brain constructions in string theory. So you know the n equals 4 theory is the low energy physics of D3 brains in string theory. And we can imagine that these D3 brains are ending on some other brains. So specifically, if we have D5 brains in some directions and NS5 brains in some directions, and then the D3 brains end on those, then that is a supersymmetric configuration. And then actually in this configuration, we can actually add more D3 brains of some finite extent in this vertical direction that start and end on different 5 brains. Okay. And so by controlling the number of these extra D3 brains, we can actually get as many degrees of freedom as we want on the boundary. And so we could make this like the effective central charge or the number of degrees of freedom of this 3D theory arbitrarily large relative to the n equals 4 theory. Okay, and so that's what we wanted from before. In the end, I want to take the n equals 4 theory, but with relatively few degrees of freedom, and then have many degrees of freedom for this 3D theory and have that be a normal holographic theory. Okay, so one of the nice things about this particular class of theories is that all of these have known gravity duals. So if we're just sticking with one boundary like this, and we look at the vacuum state of such a theory, then there are explicitly known type 2b supergravity solutions. And so looking at these solutions, then we can understand better what this end of the world brane that I was talking about is. Okay, so in these supergravity solutions, maybe I'll, let me skip ahead to this picture. Okay, so in these supergravity solutions, what you have is a part of ADS5 times S5. So this is like the Poincare coordinates of ADS5 times S5. And this would be like slicing at different Poincare angles. And so because the n equals 4 theory is then only on a half space, then the asymptotically ADS5 boundary, it's just half of the usual Poincare ADS. And then you see there's this, what I'm calling the end of the world brane. It's really like a region of the 10-dimensional geometry. So what happens there is that in most of the geometry away from the end of the world brane, it looks like ADS5 times S5. But then as you approach the end of the world brane, the S5, what happens is that it kind of puffs up, it starts deforming and it puffs up into a larger geometry, and then it pinches off smoothly. So the internal space actually has quite a bit more volume in this end of the world brane region. And then the S5 is like a little tube coming off of that. And so you can understand that, that mostly the physics within this end of the world brane region, if you had some excitations, it mostly just stays there. And then, very rarely it can leak off into the S5. Okay. And so there's this 10D picture of the gravity localization that I'm talking about. So you should really think of the end of the world brane geometry as, not specifically a brane, but it's more like a geometrical region. It's related to the physics of string theory branes, but there are a lot of those branes, and so so it's been geometrized.
So Mark, this is a Euclidean solution or a Lorentzian one?
So this is a Lorentzian solution.
Okay.
That I was describing. Although, yeah, I guess you could analytically continue along one of these directions. Okay. Okay, so what I want to do, that's just the single brane solution. So those end of the world branes, they just go off forever, and they have an ADS4 geometry. But now I want to add a second boundary. And so in this case, I have two choices. From the string theory picture, I could add the same theory again on the other boundary. So that's by that I mean that I could imagine a similar configuration of branes at the top with the same orientations. And then that whole thing would preserve supersymmetry. But that example is one where the whole theory is actually going to flow down to a conformal field theory in the infrared. So everything, the supersymmetry is preserved, and the 3D infrared theory is also a conformal field theory. Okay, so in this case, if I preserve supersymmetry, the geometry looks like this, where the two end of the world branes, they just go off and they never connect. Okay, so that's not what we want. It's sort of interesting though. Actually, it's an example of what Takinagi and others recently described as wedge holography, that you could have a 3D theory dual to, say, a wedge of a 5-dimensional spacetime. So this is a specific example of that. And actually, these geometries, that duality between the 3D theory and this wedge of 5D spacetime was studied previously by Bacchus and Lavdas. Okay, but what we actually want is different. We want these branes to connect up. And so in order to achieve that, what I do is couple the n equals 4 theory at the other boundary to a superconformal field theory with the opposite orientation. And so this boundary condition would be the one associated with the D3 branes ending on 5 branes with the opposite orientation to the one up here. So you take individually boundary conditions that would preserve half the supersymmetry, but it preserves a different half of the supersymmetry in each case. Okay. Now in this case, with all the supersymmetry broken, my expectation is that this theory is not going to have any special IR fixed point, that it will just flow to a gapped theory. And the bulk picture of that, I want to argue now, is that the end of the world brains connect up. And so I want to motivate that actually by some of this brain physics that I mentioned earlier. Okay, so I'm going to step back from this more complicated configuration where we have D3 brains ending on 5 brains, and just remember a little bit of physics of the situation where you have a bunch of D3 brains which are intersected by some 5 brains, just by a pair of D5 brains. Okay. And so in the field theory picture, this corresponds to the n equals 4 theory with some parallel defects. And if it's D5s with the same orientation, then the whole thing preserves supersymmetry. So we have these 2 defects. The full theory preserves half the supersymmetry of the n equals 4 theory. And people understood that in the dual picture, when you only have this one D5 brain, then that corresponds to having a probed D5 brain coming from each of these defects that extends into the ADS5 times S5 spacetime. So you just get these parallel D5 brains that extend into this spacetime, and they don't connect up. On the other hand, if you consider defects with the opposite orientation, so a D5 brain defect here, and then another defect with the opposite orientation so that it together breaks the supersymmetry. So then the picture is that you have a probe brain coming from each of these, but that probe D5 brain has the opposite orientation on the top and on the bottom. And so now, because it's a probe brain, you still have this solution, but it turns out that one would not be stable. The D5 and anti-D5, as they extend into the bulk, the proper distance between them actually gets closer and closer. And so at some point, there's a tachyon that develops. And the end point of that, and so that's associated with an instability, the end point of that instability is this picture where the defects join together, okay, where the 5 brains join together. Oh, yeah,
Mark,
is there a question? Go ahead.
Yeah,
Hi.
Yeah, please go on.
Yeah, no, my question is, I guess, very naive. Why is SUSY broken when you have opposite orientations?
Yeah, I mean, this is just sort of a standard string theory story. If I have brains and then I have anti-brains, then they each preserve sort of half the supersymmetry, but it's the opposite half. So you kind of just look at specifically which supersymmetries are preserved, and if I do an orientation reversal, then the supersymmetries that are preserved are the opposite ones.
All right, thanks.
Okay. Was there another question, or?
Yeah, again, probably a naive question. So so you wanted actually this to end of the brains to connect in time, but not in space, right? I mean, but here they're connecting on a time slice.
Yeah, that's right. So this picture, we're ultimately going to have sort of a double analytic continuation of this picture, right? So in this picture, we're just imagining that this is a Lorentzian theory and that everything I'm drawing here is some time slice. But then we could imagine now analytically continuing along one of the brain directions so that everything is then Euclidean. And then finally, we could imagine doing the thing where I slice that Euclidean path integral in half. So I could do that. Actually, let me, I think I have a.
Yeah, I understand. So you will have some kind of 2 asymptotic DS regions in that case, or we do this?
Yeah, I mean, in this defect theory, if I let me see, I think I have a pen. Okay, so if I were to slice this in half, okay. So if I'm in the Euclidean picture, and then I put one of these defects in the Euclidean past, so then what that does is it generates a state, which is no longer the vacuum state of n equals 4 theory. So the defect has the effect of creating a brane in the bulk spacetime. And so the Lorentzian geometry that I would get by if I make this state, the Lorentzian geometry that I would end up with is an analytic continuation of, well, it's like you take this slice that I've drawn on the right here, and then you use that as the initial data. So the initial data in the Lorentzian picture, it has this brane at some point in the radial direction, and actually in the Lorentzian picture, that brane ends up, it doesn't go towards the boundary; it goes away from the boundary. And so there's the Lorentzian picture here is that you have a probe brane with some time-dependent geometry. And actually what you find is that the metric on that probe brane, actually it is an FRW sort of metric. So the further when it is further in the bulk, the scale factor is smaller. And so you find that indeed, if you look at this kind of state, you get a probe brane inside of Poincare ADS, where the probe brane geometry is an FRW cosmology, but there's no gravity localization. So it's not useful for cosmology, but it's very under control, and it kind of gives you an idea of how to see the cosmological physics emerging.
I see.
But,
thanks.
Yeah, but so now we're just going to take this whole picture, and instead of having the probe brane, we go to this situation where, let's see, I have to get rid of, okay, let's get rid of that. Yeah, so we go to this situation where now my D3 branes end on these D5 branes. Okay, so now instead of like a single probe brane in ADS 5 times S5, what we have are these end of the world branes. And so that you can think of that as like a version, you can imagine going between these, like first imagine having more and more 5 branes, and then having some of the D3 branes end, and so forth. And so what I would argue is that the physics is still very similar, that even when we get to the final case where you have many 5 branes at the ends, and all of the D3 branes end there, in the supersymmetric situation, you still have the branes going out into the bulk and not joining up. And in the supersymmetry breaking situation, you have the branes. Now these are, like geometrized versions of D5s and NS5s, and so this geometrical end of the world brane sort of joins up in the infrared, or at least that's the prediction. Okay, so that's the picture. It's interesting to mention that this is kind of like Witten had this model of confining gauge theory very early on in the ADS CFT literature, where he said take a conformal field theory, compactify one of the directions of that conformal field theory on a circle with supersymmetry breaking boundary conditions for fermions, so antiperiodic boundary conditions for fermions. And then he argued that the dual of that has the circular direction contract in the bulk. And so here it's like that. We have these supersymmetry breaking boundary conditions, but instead of a circle, we have just an interval. And we see as you go into the bulk, the interval ends up contracting and pinching off. And it pinches off smoothly, just like in Witten's model. Okay, so that's, of course, this is, I should say, this is still like conjectural, because really what you would want to do is find this corresponding solution of type 2b supergravity. So I told you that there are solutions of type 2b supergravity in the single brane case, but there aren't the solution that I want, which has supersymmetry broken, is not known. So we sort of know what it should look like in the UV. It should look like this on one side and the mirror image of that on the other side. But we don't, like, I guess it's a hard problem to actually solve the type 2b supergravity equations to try to see this solution where the things join up. Okay, but maybe it's possible, or maybe it's at least numerically possible. Okay, So yeah, that would be important. It'd be nice to verify that. And if you had that solution, you could ask if is the least action solution, does this gravity localization persist, and so forth. Okay, so that's the basic story. I'll just then summarize everything. And so the idea is that we want to start with a picture like this, where you have a pair of 3D CFTs coupled together by a 4D CFT. And we want to take that 4D CFT to have many fewer degrees of freedom than the 3D CFTs. Nevertheless, we expect that in generic cases like the supersymmetry breaking case that I talked about most recently, the IR physics of this theory is going to be gapped. And at least in some cases, I expect that the dual gravity picture of that gapping is that you have some end of the world brains and that these join up in the infrared. Okay. And so this could be a Lorentzian picture of just a regular field theory with some boundaries. In that case, this end of the world brain, it would actually be like a Lorentzian wormhole between two sides. But what we're interested in is the Euclidean continuation of that first. Okay, so if this picture represents a Euclidean field theory, then this would be a Euclidean asymptotically ADS wormhole. And then what I want to do to connect with cosmology is actually really use that Euclidean field theory construction, slice it in half in order to produce a state of this 4D CFT. So that produces a very special state of the 4D CFT. And the gravity dual of that state I get by slicing this Euclidean geometry in half and then using that as the initial data. That ends up giving you something that looks like this in the space-time diagram. And so now we're back to the final story where you have something like a black hole, or the initial story, we have something like a black hole space-time. We have this end of the world brain, which is behind the horizon. Its geometry is a 4D Big Bang, Big Crunch cosmology. And then hopefully the fact this condition on the degrees of freedom will help ensure that you have gravity localized there. Okay. And if this 4D theory is not really a holographic theory, then maybe this whole bulk region, this whole 5D region might be strongly curved. And hopefully then it's just like a small perturbation that wouldn't be noticeable in say our measurements. Okay. So I guess the exciting part about this, if it works, is that you would have a fully microscopic picture that would realize cosmological physics. And so then you could just start with the microscopic setup and you can ask any questions that you want about the cosmology, like, what is the evolution of the scale factor? How does the stress energy tensor evolve? Is there a cosmological constant? How does that change? What are the density perturbations and so forth? So these are questions that I'm currently trying to investigate with various people at UBC and other places. So thanks for listening.
Thanks a lot, Mark, for this wonderful seminar. So we should take questions now. So please unmute yourself and ask questions. So I actually have I have some questions still regarding the initial part, what we were talking about, what I was asking. So this picture, this double analytical continuation picture has some state, is a statement that one can make in the context of the CFT itself. The CFT picture, the two 3D CFTs connected by 4T.
Yeah, so let's see. I mean, so I guess there's three pictures. One of them is the picture that I've drawn, but now just interpret this as a Lorentzian field theory with a time. And then, so that would just be describing some ordinary field theory on a strip. And so that's the picture that you would really say is like a confining or gapped 3D 3D gauge theory. And in that case, the gravity dual is this geometry, but in that case, the geometry is static. Like there's a what I've drawn is the spatial geometry. There's some time direction as well, but nothing changes in time. So it's like a static geometry. There's an end of the world brain in that geometry where gravity is localized. And so what you would have in that case would be like you'd call it a eternally traversable planar wormhole. Okay, then we analytically continue this time direction so that everything is now Euclidean, and then it's like this confining Euclidean gauge theory. Okay, and then the final step is kind of to analytically continue in the direction between the two boundaries, and really there, what I'm doing this sort of slice of the path integral, and so in the end, like the physical theory doesn't really have the degrees of freedom of these 3D CFTs. It's kind of a weird feature of it. The 3D CFTs in my final picture, they're only there to help create this interesting state of the 4D CFT. And
but you also need to create a final state, right? I mean, this is
well, I guess it's just a state in the Hilbert's. I mean, it is a state. I can think of it as maybe in the Heisenberg picture. It's just a state in the Hilbert space of the n=4 theory on either R3 or S3. And,
yes,
and that state, it encodes this full time dependent geometry, if you want.
Okay, I see. I understand. So I understand. So now, yeah, somehow okay, it might be very naive again. So I don't understand how these two 3D CFTs are coming together in this, when you do this analytic continuation. You see, this is what I getting confused about.
You mean how this connects up in this picture? Or
yes, once we do this double analytic continuation, I understand this picture now, but somehow there was some green brain. So you have two red things coming together in this last picture. You said talked about three pictures. In the last picture, the two red things come on top of each other. It's just that how they come on top of each other is what confuses me a little.
Oh, sorry. Are you talking about this picture?
Yeah, exactly. So when you connect the top picture with the bottom picture, the picture that in the summary just so how these two red things
so
are
the connection is, I mean, basically the similarity is the thing that is the same is like this slice here. So that's a spatial slice of a time dependent geometry that agrees with this slice here.
Mm-hmm.
Okay, so you see if I take this slice in the Euclidean geometry, then it's got an asymptotically ADS region. And then as I go in, eventually I get to the end of the world brain.
Okay, I understand. So
and
basically,
so that is now the initial data here.
So
but
I
if
see
I
it's
evolve
like, I understand. Now I understand. So it's like two halves. One half goes, the top half goes to the upper half and the bottom half goes to the lower half, I see.
Yeah, I mean, it's kind of like this Hartle-Hawking picture, if you're familiar with that. Like you have a Euclidean geometry that you can then sort of glue on to a Lorentzian geometry.
So it basically, the reason it works is time symmetric, because the upper one goes to the upper half and this thing, the lower half. Okay. The time symmetric is the key. Yeah, right here.
Right. That's right. Yes, that's right. So that's why I don't know how to get, if I just want a big bang, but not a big crunch, then I'm not sure what.
I see. But of course, this is a very specific assumption, because time symmetry itself is a very strong assumption, irrespective of whether there's a big crunch or not, right? I mean, we can have an asymmetric
That's right. That's
big crunch also. I see. Okay, so but the other thing is that, is there any statement that you could make about some entanglement in the first context? Say I take a entanglement between the two CFTs, 3D CFTs, and that turns out to be some sort of a correlation between past and future here. I mean, what is there some way one can make some comment here?
Yeah, that's a good question. So, so you mean in this Lorentzian picture on the top.
Yes.
Yeah. So there's a very interesting point, which actually we've just realized recently, which is that certain observables in this picture, in this kind of static Lorentzian picture, they probe that they correspond to other observables in the cosmology picture. So, indeed, basically because this geometry, like this time equals 0 surface here, is also part of this Euclidean geometry, and then that's also sort of it's part of the dual of this. So the dual of this thing is a static geometry, but it sort of shares the same slice with this guy. And so, it's indeed interesting to ask, if you compute observables in this confining gauge theory, I don't know, like the one you mentioned. I don't know that we've particularly thought of that one, but yeah, say we compute entanglement entropy between some top and bottom, then that should probe the Lorentzian version of this picture that should tell us about the geometry of this end of the world brain. But that should also tell us some things about the geometry in this picture. So I think this is an interesting, like, you can ask, well, how do we go and actually learn about this cosmology because it's behind this horizon? Well, one of the answers is that this geometry has the same slice as this one, and we can learn about that using this picture where the end of the world brain is not behind a horizon because it's static. So that's very, I think, very, very interesting, but we're just kind of beginning to explore this.
I see. Okay, so that's interesting. And another again, very naive question again. So is this whole thing consistent with like causality when we do this double analytic continuation? So maybe the time symmetric thing is a key that make it work, but for example, suppose if I compute correlation functions in this by using this double analytic continuation method, would it remain causal?
I mean, I'm not sure precisely what you mean, but I think so. The notion of causality in the first picture is different than the notion of causality in the second picture. So
yeah, exactly. So that's what
I think they both have different notions of causality, but
yeah,
I think both would seem to be conventional theories preserving causality. So
right, because this is of course a general question that was that I have about analytic continuation in general, but maybe when it works, it should be consistent. It may not always work, but whenever it works,
yeah,
I see. So it should reproduce the it should be causal in both cases. In that case, yeah, of course, yeah. And so the final question is that in this context, what would you be able to like, you probably this is something that you are working on maybe, but if you ask something like inflationary scale invariant perturbations, does it come out naturally here or not?
Yeah, I mean exactly. This is a kind of question that we're trying to think about right now. So it's not I don't have an answer yet, but one could ask. So it's not clear. Like, okay, we don't know exactly what the solution is in some examples. So I don't even know if there might be an inflationary phase or not. But in either case, you can still ask what the correlations between density fluctuations are, and we should be able to ask in these models, is it sort of similar to the projections of inflation, or is it something very different? So yeah, I think these questions are, at least we can understand how to set them up, or how to ask them as field theory questions.
And the other thing in the diagram that you drew in the bottom, it seems like the red brain is going to see the whole asymptotic region at some point. It is not the whole. I mean, if you're going to see the sorry, what I mean is that it is going to see a part of the other green region. Yeah.
So that you mean sorry. You mean that you would have some light rays that get to that.
Getting to that, what
yeah,
what
I
is
guess
it,
so. Before the I guess before the universe ends, someone from the asymptotically ADS region could send a signal to say, hey, you live in an asymptotically ADS universe. But
it looks like
other
that,
than that, I guess we're still here in the expanding phase, so we've got a long time before we realize anything.
But my puzzle was that this has no analog in this upper picture.
I mean,
analog.
again, right. So the time evolution in this picture doesn't have much to do with the time evolution in the top picture, or it would be, some very complicated analytic continuations to see that.
I see. But this is something totally new feature that there is one couldn't have guessed from the analytically continued version of it.
Yeah, that's right. Yeah. So I don't know if it has anything. I don't know if there's some interesting consequence to that. But.
Okay. So
hi, can I ask a quick question, please?
Of course.
Yes,
of course.
please.
Yeah. So this is actually a vague question, but I apologize in advance, but I'm very curious to know. So, I mean, can this physics exercise be have an analog in can it be equivalently worked out as a math exercise in the following sense that can one study a theory of cobordisms between three folds which are connected by a fourfold which has the two three folds the disjoint union of these pair of three folds forms a boundary. Can there be some kind of a well-posed problem as a theory of cobordisms here?
Yeah, I don't know. I don't know if I have anything useful to say. I mean, I'm not sure if there would be an analog of sort of these. So there, I guess it would be more like a Euclidean story.
Maybe naively, if this whole thing somehow, if it could be lifted to F theory, can one study this as a theory of cobordisms? It's just a vague question, but I'm very curious to know.
Yeah. So, I mean, I'm not sure. I'm not sure. I probably don't have a useful thing to say other than that. So the geometries are. So these 10D geometries are very interesting. These 10D geometries would have some F theory interpretation, but I'm not sure if that would connect with your original question. Yeah, I probably just don't know enough about that field of math. Yeah.
Okay, if there are no more questions, then let's thanks Mark again. Thanks for this great seminar, Mark. We really enjoyed this, and it was thanks for giving us a very good time. And
great. Thanks for all your questions. All right.